about some work that's also much work and in progress. So today in the exercises there was a bunch of exercises about finding null pointers, and this is one of, I think, the classic Coccinelle. Could you stop? Oh. This is one of the classic Coccinelle patterns that tries to find null pointer dereferences. So how can a pointer become null? Well, it might come from malloc, or it might come from calloc, or it might come from realloc. And then if we don't check it whether it's null, then it might be null when we try to do some kind of dereferencing. But in reality, there's a lot of other ways that a pointer can become null. Maybe we call a function that calls a function that returns null, as Julia talked about. Or maybe we have maybe we have an alias to this pointer. So in reality, x is not changed, but a pointer to x is changed. So this is quite hard to describe on the syntax level. So our initial idea was that what if we had this kind of black box which could tell us whether a pointer might be null. And this black box might come from some kind of program analysis, some kind of classic program analysis. So if we had this kind of black box that could tell us whether a pointer might be null, then we could integrate this into the semantic patch in some way. And this is more or less just, this is an idea for how the syntax might look. So basically, what we would like to do is have this analysis whether a pointer might be null, and we call it something. And then we can have these different kinds of ways of dereferencing a pointer. And then we say, is this location we find, is this in the null pointer analysis? And if it is, then we might have a null pointer dereference. So another direction we might want to go is to do this more precisely, because we know that the variables can be aliased in C. So we might have two pointers to the same value. So if we do this, then if we had a black box again that could sort of say these two variables might point to the same memory location, then we could use this to look for box where we use something after 3 in this case. So basically this pattern is, again, we look for some call to free, which frees the variable x, which might be aliased to other variables. Then we look for some kind of control flow where we do not assign a value to this other pointer y. And then if y is somehow used, then y might still point to the value we just freed. So in this way we would be able to find more true positives. But of course, using these kind of analysis information, the information we have from the black boxes, from the program analysis, they of course are not sound and complete. So we get some more false positives.
The x and y, do they mean something in alias? We have x, y, alias, so is there some connection with the x and y identity?
Maybe not. I mean, this syntax is in no way implemented. So, I mean,
maybe you could do alias and then parentheses x,
yeah,
something like that.
I mean, the current implementation we have is relying heavily on the Python scripting abilities. So we have not made any kind of nice syntax for it. We just have some Coccinelle patterns and then some big chunks of Python doing stuff.
But to answer your question, no. It's just a name.
So one area where we looked is there's actually this standard for secure C code C programs called the CERT C standard. And it has a bunch of categories where there are different patterns. So it has some patterns for the preprocessor, for declarations and initializations, for expressions, for memory management, and a lot of other stuff, and miscellaneous. And the problem is that some of the patterns are universal. Like there's a pattern which says do not dereference null pointers. We know that that's a universal pattern. Do not access free memory. No, that's also universal. But then we have some patterns that need to be customized to the project in question because they simply depend on what kind of project you're doing. So for example, there's a pattern called detect and handle errors. Errors in the Linux kernel are handled very differently from errors in a user space program. So this means that we cannot simply make one set of patterns and say this is enough for everybody. We need for people to be able to customize the patterns to fit their specific project. And a lot of the patterns can be analyzed more precisely if they are customized. So some of these patterns are like rules, but actually most of them are just recommendations, and most of the recommendations are project specific. So what we learned from looking at this CERT C standard is that there are a lot of universal truths about good C programs or secure C programs. It very much depends on your project. So you need a tool like Coccinelle where you can actually fit the tool to the project instead of fitting the project to the tool. So we did some initial work in this area of trying to integrate some analysis information, some program analysis information into the Coccinelle framework. And we ran into a lot of dead ends. So our initial idea was to take the Clang C compiler, which is developed on top of LLVM, and I think it can almost compile the Linux kernel or something like that. But initially we had hoped that we had some analysis information available from the Clang C compiler that we would be able to readily use in our Coccinelle scripts. Unfortunately, because Clang uses this low-level virtual machine, it doesn't actually have a lot of analysis of its own. It relies on the analysis on the low-level virtual machine layer for most of the things it does. But it does have some simple analysis. Among others, it has some kind of a pathway symbolic execution analysis, which basically tries to find bugs that are surely bugs. It tries to find out whether, so in Coccinelle whenever you write ... it means any kind of control flow. This also control flow that might not happen in real world executions. But this symbolic execution engine, it tries to find execution traces that actually will happen. It also has some very simple program analysis, some simple classic program analysis, but for our purposes they are very much hard-coded to the purposes Clang needs. On the positive side, the error reporting from Clang is really, really nice. When you run Clang as a program analyzer, you get a website where you can actually see the different bugs it has found. And you can see how the control flow will be. But yeah, we want to integrate this Clang or some analysis information from Clang into Coccinelle. But we couldn't use any of the analysis that Clang had. So we had to develop our own analysis on top of Clang. So our initial idea was to use a formalism called weighted push-down systems, which basically is just a way to do program analysis that is quite fast and quite precise, because you get this interprocedurality that Julia talked about for free. And we actually got something working with that, but the problem is that the thing we got working is basically not very well integrated into Clang, and it's hard to see it ever being really integrated into Clang, because actually there is no purpose of it in Clang. It is specifically for our purpose. So, yeah. So our current idea is that instead of doing our own thing on top of Clang, we would like to use Clang as a library instead. So the idea would be to use the Python scripting framework of Coccinelle to get another view of the program from Clang, but integrate this at the Python layer. So currently we are developing Python bindings for Clang, such that we will be able to access the internal data structures that are in Clang that has a lot of the information that we want to have. Like, for example, how structs are packed, or how Clang is going to pack these different structures. And because we are going to integrate the two different worlds at the Python level, there is a much greater chance that the Clang developers will actually think it's a good idea to have Python bindings for their project. And of course, we already have Python bindings in Coccinelle. So our current findings is that Coccinelle is a very potent bug hunter because of its customizability, because it's fast and it's usable. But if we just had a bit of program analysis information, it would be much more nice. So our current work is to develop these Python bindings for Clang and actually get some patterns up and running. And when we have some basic patterns up and running, we would like to get more analysis information. For example, this aliasing information. But the integration doesn't have to be only one way. So one thing that would also be nice is if we could somehow integrate Coccinelle into the building process of a project, basically into the makefile. So as I mentioned, Clang has this very nice error reporting, and if we could find a potential bug using Coccinelle, we could feed this into the Clang framework using this symbolic execution engine to actually get sort of verified that this is actually a bug. And when we do this, we will be able to use this error reporting from Clang. So in essence, the project developers will only have to look at one error reporting user interface. So yeah, more integration both ways. Yeah. Any questions?
How far are you been looking into this CLang and print out the structures and having all the offsets? Is that something almost done? Or?
Well, I mean, the problem is, Clang is a big C++ project, so if we just wanted to have like the layout of the structures, then we would quickly be able to hack that in. But this was sort of our first approach, and this was not a very good approach. Okay. Because we would like a more long-term solution that the Clang developers would actually like. So that's why we're going the Python bindings way at this moment.